My name is Enyu and I'm from TC02. So before my teammates present their calculations, I would like to further elaborate what dynamic partitioning means. So dynamic partitioning, also known as variable partitioning, means its partitions are of variable length and number. So in contrast with fixed partitioning, this technique allocates processes exactly as much memory as it requires. However, it eventually gets holes in the memory. This is called external fragmentation. So what external fragmentation does to the memory is it makes it more and more fragmented, and the memory utilization will eventually decline. Therefore, for this technique, compaction must be used to shift processes so that they are contiguous and all free memory is in one block. So compaction is a technique for overcoming external fragmentation. As stated, it enables the operating system to shift processes so that they are contiguous and free memory is together in one block, though the downside is it's time-consuming and wastes CPU time. So in order to overcome these problems, the operating system must decide which free block to allocate to a process. That's where dynamic partitioning placement algorithm is practiced. So for the first technique, the best fit algorithm will choose the block that is closest to the size to the request. However, it's the worst performer overall because it consumes a lot of time searching for the whole memory for the requested block. Since the smallest block is found for a process, the smallest amount of fragmentation is left. Therefore, memory compaction must be practiced more often. The next would be first fit algorithm. So for first fit algorithm, it scans memory from the beginning and chooses the first available block that is large enough. It's the fastest in processing because the processor allocates the nearest available memory partition to its job. It's very fast in execution. However, this may result many processes loaded in the front end of the memory that must be searched over when trying to find a free block. The last algorithm would be worst fit algorithm. For this algorithm, it scans memory from the location of the last placement, and more often, it allocates a block of memory at the end of the memory where the largest block is found. So if a large process comes at a later stage, then memory will not have space to accommodate it. Therefore, the largest block of memory is needed to be broken up into smaller blocks. So compaction is required to obtain a large block at the end of the memory. So this is all for dynamic partitioning placement algorithm.
Hi guys, my name is Sean. I'm from TC02 and today I'll be showing you how to solve a dynamic partitioning placement algorithm. So for our first question, we have a memory configuration of a dynamic partitioning scheme, and this is the process numbers that we'll be using to solve our dynamic partitioning scheme later, and this is the size of the process numbers but in kilobytes. So we'll be solving in two ways. First way will be the first fit, and then later on will be the best fit. So what is a first fit algorithm? So a first fit algorithm is the simplest technique of allocating the memory block to the processes amongst all. Using this algorithm, the pointer keeps track of all the free blocks in a memory and accepts the request of allocating a memory block to the coming process. It starts scanning from the beginning and looks for an empty free position as long as it's big enough for them to fit in. It starts scanning from left to right. The first fit algorithm is fastest but not necessarily the best way, and the first fit algorithm may have many processes loaded in the front end of the memory that must be searched over when trying to find a free block. So first, here we have our memory configuration of the dynamic partitioning scheme. First, we combine the holes that have no partition in between them. So the ones that have U stands for used and have no spaces inside for a free block to move in, but the ones with H they're called holes and they have spaces inside them. So the first thing we have to do is we combine the holes that have no partition in between them. For example, these two holes have no partition in between them, so there's these two holes, but this hole has a partition, is in between two partitions, so we can't combine this with anything. This will be alone, and so will this. So when we combine the holes, we'll start with H with 30 minus 10, so 30 minus 10 is 20, so this hole will have 20 free spaces inside it. And H, these two H's that we have to combine, they will, okay, so the way we calculate this is we take this number 150 and we minus the number that the hole starts with, which is 100. So, and we will get 50. So this hole, after combining, will have 50 spaces, 50 free spaces inside of it. Now for the second hole, we have 273 and we'll minus 225, and that gives us 48. So this hole will have 48 free spaces. For the last hole, we have 480 minus 360, which gives us 120. So now after combining this, these are the values of the holes. So after doing the first step, which is combining the holes that have no partition in between them, we move to the second step, which is finding a hole that is large enough for each processor. So we start with processor number 1, which has 12 kilobytes which is 12 kilobytes in size. So now since this hole has 20 and it's closest to the left, we can place the process 1 inside this hole. Process 1 will be inside here, so the remainder will be 20 because the first hole has 20 spaces, minus 12, which is the size of the processor. And that leaves us with 8. So we'll put 8 here as the remainder of the free spaces in this hole, and this will just bring down the values, the other values will just bring it down. Step 3 is finding a hole that is large enough to fit process 2 inside, and process 2 has a size of 22 kilobytes. So now again, we'll look for a hole that can fit 22 kilobytes inside. So the first hole can't because it only has 8, but the second hole it can. So process 2 will go in the second hole. So first we'll bring down the values, 8, and since process 2 can go into the second hole, we subtract the second hole, which holds 50 free spaces with the size of the second processor, which is 22, and that leaves us with 28. So process 2 will be here, and the remaining space of the second hole will be 28. And then we'll just bring down the other values that we have not touched. Now for the fourth step, we'll find a hole that is large enough to fit process 3 inside. Process 3 has 32 kilobytes in size. Now we'll start scanning from left to right to see if 32 kilobytes can fit in any of these holes. So the first hole can't because it only has 8 spaces. The second hole can't because it only has 28. But the third hole can because it has 48 spaces and 32 can go inside this. So we'll just bring down these values. And now we know that 32 can go inside 48. So to find the balance of this hole, we'll subtract 48 with 32, and that will give us 16. So our value in this hole will be 16. And we just bring down the other values that we have not touched yet. So now for the fifth step is to find a hole that is large enough to fit process 4, which has 75 kilobytes, and we also start scanning from the left to right. Hole 1 is too small, hole 2 is too small, the third hole is too small, the fourth hole is big enough, and we bring down the values of the holes that we are not going to use for this step. So now we're going to use the fourth hole, which has a 120 free spaces. So to get the balance of this hole, we take 120 and we subtract by 75, and that will give us 45. So now processor 4 goes here before the fourth hole, and the fourth hole has the balance of 45. Now for our final step, we have to find a hole that is large enough to fit process 5 inside, which has 9 kilobytes only. So we start scanning from left to right. Hole 1 is too small, but hole 2 is big enough. So we bring down the values of the holes that we're not going to use. And now we add process 5 inside this hole. Process 5 has 9 kilobytes and this hole has 28 spaces. So to get the value after adding process 5 into this memory configuration, we take 28 and we subtract it by 9, and that will leave us with 19. And now we put 19 here because 19 is the number of free spaces that we have left in this hole, and we bring down the other values that we never used for this step. So 16 will be here, and 45 will come down here. So that's how we solve this memory configuration using the first fit algorithm for this dynamic partitioning scheme. So now I'll be talking about the best fit algorithm. What is the best fit algorithm and how does it work? Well, the best fit algorithm works by allocating the smallest free partition which meets the requirement of the requesting process. This algorithm will first search the entire list of free partitions and it will take the smallest hole. The best fit algorithm is actually the worst performer overall, and there are three different types of algorithms, and the best fit algorithm is actually the worst performer among these three. And since the smallest block is found for process, the smallest amount of fragmentation is left. So the balance in each holes is called the external fragmentation, and using the best fit algorithm, the smallest amount of fragmentation will be left in each hole. And memory compaction must be done more often for the best fit algorithm. Now we'll take a look at the examples and how to do the best fit algorithm. So in the beginning, it's the same. We have to combine the holes that have no partition in between them. We have to combine these two holes and these two holes. So this hole will have a value of 30 minus 10, which will give us 20. And how do we combine these two holes again? 150, we take this value and we subtract it with this value. We take 150 and we subtract it with 100, and that will leave us with 50. So the number of free spaces for the second hole will be 50. Now these two, we combine it by taking 270 and subtracting it by 225. So we'll take 273, subtract it by 225, and that will give us 48. So the size of the third hole will be 48. And finally our last hole will take 480 and subtract it with 360, and that will give us 120. And now we go to the second step, is finding the hole closest to fit process 1 inside, and process 1 has 12 kilobytes inside of it. And now we find the hole that has the closest number to 12, and that closest number will be from hole 1. Hole 1 is 20, it's closest to 12, and we'll add process 1 into this hole. We'll add process 1 here, and the balance of space in this hole will be 20 subtracted by 12, and that will give us 8. So the balance here will be 8, and the holes that we have not touched using this step, those values in those holes, we'll just bring it down. We won't change it, we'll just bring it down. For the third step, we find the hole closest to the fit for process 2, which has 22 kilobytes. It's this big, and this is the size. So now we look for a hole that has 22 or close to 22 free spaces. Hole 1 does not have 22 spaces, it only has 8. 50 is quite big, and hole 48 is the closest to 22. So we'll bring process 2 and put it inside this hole, and the balance of this hole will be 48 minus 22. So we'll get 48 minus 22, and that will give us 26. So like just now, the holes that we don't touch, we have not touched, we just bring down the values. So 8 here, 50 here, and now we add 26 into the third hole where 48 was, and for the last hole we bring down 120. Okay, step 3 complete. Now going on to step 4, we find the closest hole to fit process 3, which has 32 kilobytes inside of it. So which is closest to 32 kilobytes? 8 is too small, 26 is too small, 120 is too big, but 50 is just nice. So we bring down the holes that we're not going to use, the value of the holes that we're not going to use. And now we're going to use 50. So we add process 3 here into the second hole. And the balance of this hole will be 50 minus 32. And that will give us 18. So the balance of this hole here will be 18. And we just bring down the holes that we have not touched, the values of the holes that we have not touched. And now we move on to look for the closest fit for process 4. Process 4 is 75 kilobytes in size. And now we look on top here to see which will be the closest fit for process 4, which hole. So we look at the first hole. The first hole is too small, second hole is too small, the third hole is too small, but the fourth hole is big enough and it's the closest fit for process 4. So we bring down the values of the holes that we're not going to use for this step. We just bring it down, we don't change anything. And now we have 120 here. So we put process 4 here, and the balance will be 120 minus 75. And that will give us 45. So the remainder of this hole will be 45. Now we move to our last step, which is finding the closest fit for process 5. And process 5 is 9 kilobytes in size. And the closest fit, if we look up here, is not the first hole because the first hole is too small. It's the second hole because it's bigger than 9. These are all bigger than 9, but this is the closest to 9. So process 5 will go into the second hole, and the holes that we're not going to use, we bring down their values. And now process 5 is 9 kilobytes in size, and the hole here is 18. So we take 18 and we subtract it by 9, and that will give us 9. So the balance for this hole here will be 9, and we just bring down the values of the holes that we have never touched for this step. And so that is how we use the best fit algorithm in this dynamic partitioning scheme. Thank you.
Okay, now we'll be moving on to question 2. Here are the memory configuration of a dynamic partitioning scheme being used. So there are 5 holes here, hole with 30 size, 45, 50, 90 and 125. The following process requests will be received in order. So process 1 is in 35 kilobytes, process 2 in 20 kilobytes, process 3 in 15 kilobytes, process 4 in 80 kilobytes. I'll be showing you 2 ways for the memory request above to be allocated. The first one is first fit and then best fit. So first fit, here are the memory configurations. Step 1 is to find a hole that is large enough to fit process 1, which is 35 kilobytes. So we look at the memory configuration here. The one that can fit 35 kilobytes is 45. So all we have to do is 45 minus 35 and we get 10. 10 is the remaining for the size of the hole. And then we fit process 1 here. So 100 until 135 is equal to 35 kilobytes. Then step 2 is to find a hole that is large enough to fit process 2, which is 20 kilobytes. 20 kilobytes, so we look at here. 30 is the closest one. So we use that, so 30 minus 20 equals to 10. So 10 remaining in the hole, and then process 2 will be inserted here, where 30 minus 10, 20. And then step 3 is to find a hole that is large enough to fit process 3, which is 15 kilobytes. And the closest one we can get is here, at hole 50 here. So therefore 50 will be minusing by 15, equals to 35. So we have the remaining here, 35. We have P3 over here. 250 minus 200 equals to 50 kilobytes. And then lastly, step 4, find a hole that is large enough to fit process 4, which is 80 kilobytes. And the closest one we can see here is at here. This hole contains of 90 kilobytes. So therefore 90 minus 80 is equal to 10. So the remaining is 10, and insert the process here. 560 minus 480 is equals to 80. So that's the size of the process. Moving on to best fit algorithm. Here are the memory configurations again, same as the one above, just a different way. So step 1 is to find the hole closest to fit process 1, which is 35 kilobytes. So again, closest one here is 45. The whole 45 minus 65 equals to 10. 10 is the remaining here at the hole. The process will be inserted here. Now step 2 is to find the hole closest to fit process 2, which is 20 kilobytes. So you can see here, this hole, which contains 30. So therefore 30 minus 20 equals to 10. And here, process 2. And step 3 is to find the hole closest to fit process 3, which is 50 kilobytes. Same again, we look at here, 50 kilobytes is the closest one to fit in 15, because 10 is not big enough. So 50 minus 50 equals 35, the remaining this hole is 35, and then process 3 will be inserted here. And then lastly, step 4, find the hole closest to fit process 4, is 80 kilobytes. Which means, look at here, this hole here contains 90, so 90 minus 80 equals to 10, 10 is the one remaining here, and then process 4 will be inserted here.